Okay, Bismillahirrahmanirrahim. Welcome to this session. We were discussing on different properties of the discrete signals, and hopefully we are confident enough to represent our discrete signal in the frequency domain as well from the sampling point of view. The story is very simple. I have already mentioned that you need to understand about your signal xn. It is first of all, it actually came from your continuous time signal. So from the continuous time signal, you need to choose your sampling frequency in such a way that you can have your discrete signal, and in any time you can again come back to your original signal. So you need to choose your sampling frequency based on the Nyquist theorem. And I have already mentioned that what are the complexities we may face if we choose a different fs rather than twice of the maximum of your analog signal frequency. As we have already mentioned that this analog signal, the xt, it may have a band of frequency. Let's start from the frequency from 0 to f max. Not necessarily always you have 0 hertz there. It might be, we can mention in a way that f minimum to f maximum. So in that case, our sampling frequency fs should be twice of, at least twice of the maximum frequency. So we have mentioned that. But conventionally, what we need to do, if this is our xt, we need to pass it through a low pass filter where we know the cutoff frequency. What is the cutoff frequency? C cutoff, F cutoff. So we should know that, because you have designed the low pass filter, so you have to know that what is your cutoff frequency. And this cutoff frequency is actually the maximum frequency of your band. So after having that, we can say that this is xt prime, and which have the maximum frequency, which is equals to the cutoff frequency. Now you know the maximum frequency, and now you can design your sampler with a sampling frequency is equals to double of the maximum of that. And after this, you can do the process, whatever the process you need to do, and then you can come back to your original signal back. So after having this sampling, you will find your xn. So that is the discrete signal. After doing some processing, what kind of processing? It might be any sort of digital signal processing. After that, you may come back to your original signal. And in that case, the aliasing will not make any effect. Okay. All through the lecture, we have represented our aliasing signal as a negative signal. Negative in a sense that it actually destroys the signal. It also changes the originality of the signal. However, there are some purpose of the alias signal. By using the alias signal, you can also compress your signal from the higher frequency to the lower frequency. Probably we don't have enough time to discuss about this, but you can also search it. What is the use of the alias signal in the signal processing? What I have meant that by using the alias signal, you can also represent your higher frequency signal to a lower frequency signal. Okay, so that could be a use of the alias signal in the signal processing. However, we are not discussing, or we are not asking any question on the positive outcome of the alias signal. Always we should think about the negative outcome of the alias signal. Okay, so far we have done those things. If you have any question on those topics, you can raise your hand. and I will ask you for those confusion or any comments. Okay, before going to the next topic or the continuing the topic, I'd like to discuss about the marks distribution. Hopefully you have also got the marks distribution from the university. That means what is the structure of the marks distribution. Now for the DSP, digital signal processing, for our case, how I would like to distribute the marks and what are the modality to conduct the exam. So before mid, so we have mid. So mid will carry 25% of the marks, and you need to go for a written exam. So this will be a conventional exam, online written exam. So we'll discuss about it more in future. In a final, it also carry 25% of the written and 10% for the viva. It has been mentioned in this way. For the mid, it is written, and for the final, this is 35%, 25% for the written, and 10% for the viva. Okay, fine. There is some attendance and performance. It is 10%. So you have in the final, this is 35%. In the mid, this is 25%, and attendance we have 10%. So altogether, this is 30, 40, 50, 60, 70%. And rest of those are the quizzes. It can be quizzes. This can be assignment or viva. So it's mentioned like this. So it should get total. You should get total 30% number for with a combination of quiz, with assignment or viva. So what I am planning before the mid, from the before the mid syllabus, I will go for a viva. Since in the midterm we are not supposed to take any viva forcefully by the structure. That's why I will put a viva, which will carry 20% of number. That means 20% from these 30%, and the rest of the 10% will be given to the final as quizzes. There will be 2 quizzes, so 10%. So I'll give 10%. That means it will be 10% plus 10%. However, this 20% of the viva, it can be distributed at 10% plus 10%. So 10%, 10%, 10%, 10%. So that is a 40%. So out of 40, it will be counted best 3. That will be 30%. So that means this viva actually counted as 2. It will be equivalent to 2 quizzes. Okay, it will be taken before mid, from the before mid syllabus. So the before mid or before mid or during the mid, you are not facing any quizzes. So before the mid, I will conduct a day-long viva session. You will join. So I'll discuss those things in future classes, inshallah. So there will be a schedule, so where you will face the quizzes. So face the viva, only a single viva, but that can be covered a whole bunch of syllabus from the before mid. And in the final section, you will find 2 quizzes and also viva in the final section and the written exam in the final. Okay, so that is the whole structure or the marks distribution of DSP for this semester. Okay, so this is the thing I am just discussing in front of you. If you have any question in the next class, I am not welcoming any question at this moment, because you can discuss yourself. If you have any questions or queries, we can discuss in the subsequent classes for the marks distribution, inshallah. Okay, let me start today's lecture. So we have already given the lecture up to this. So now we can move forward. There's some basic signals. You have already known about these signals in your continuous time domains. In case of continuous time domain, so we can also represent it for the discrete time domain. Some very basic signals. So number one is the unit sample signal. It is also known as the impulse signal or delta function. Then unit step signal, exponential function, and sinusoidal signals. We can represent any signal with a combination of these four signals. That's why this is known as the basic signals. Time to time, we'll discuss about those signals more. However, here we can represent all four signals with a graphical representation as well. So I believe that you know all the perception of those four signal. So this is our delta signal. It has 1 at the center, and otherwise you have zeros. You have unit steps signal like 1 starting from the 0th sample to the positive infinity, and zeros in the negative side. That is the unit steps. This is the exponential signal where this xn is equals to a to the power n, where a is less than 1 and greater than 0. That means this is a positive quantity but less than 1, and that makes this value reasonably smaller when the value of n is increasing. So if n goes to infinity, then the value of xn goes to very close to 0. So that is exponentially decayed signal. It can be exponentially goes higher value. If a is more than 1, in that case it will rise like this. So it will goes very higher value like this. So this is an example of an unstable system, and this is an example of a stable system. Okay, we'll talk about the stability of the system in future classes. And as you know that about the sinusoidal signal, we have talked about sinusoidal signal in previous classes. Now would like to represent the discrete time signals. How to represent the discrete time signals? There are different ways to represent the discrete time signals. Few of those are like this. Okay. This is a format by which you can represent the discrete time signal. This is a graphical representation. This is called the graphical representation. And this is pretty simple, where you are putting those stem. By using the stem, you are representing your signals. And we are also mentioning the values of those. And we are also mentioning the positions. What are the positions of that signal? Similarly, it can be also represented by the functional representation like this. Xn, how the xn looks like. 1, the value is 1 at the position of 1 and 3. 4 at the position of 2, and 0 elsewhere. So we can draw it like this. Okay, if I have this functional representation, I can draw the image like this. Okay, so this is 0, 1, 2, 3, 4, let's say. So at the 0th place, of course, that is at place number 1 and 3, 1 and 3, 1 and 3, we have the amplitude 1 like this. At the place of 2, we have 4, and elsewhere we have 0. Elsewhere we have 0. So anywhere it will be 0. So this is our xn, and this is the functional representation of the signal. It can be also represented as a tabular representation where n, the sequence of n is mentioned in the top side and the xn represented in the bottom side. So this is the 0th sample. We have 0 at the 0th sample, 1 at the first sample, 4 at the second one, and 1 at the third one, and 0 elsewhere. So the same function, the same xn can be represented like this in the tabular representation. It can be also represented in a sequence, where this kind of arrow represents the 0th sample. As we have already mentioned that at the 0th sample, the amplitude is 1. Now this is first sample, this is second sample, this is third sample, fourth sample, and so on and so forth. And this is -1, then -2, something like this. This is very simple. So this is how we can represent our sequences. Altogether, this will end the first chapter, or you can say this is the wrap-up part of the first chapter from the Proteus. Okay, I believe that you have already started to read the book, because whenever I am giving the lecture, I already mentioned that I am collecting the information from the books, video lectures, and the different sources. However, probably there might be some chances that I'm missing some section, important section from the book as well. So you need to read the book always. Okay, so book chapter is very important for understanding. Okay, now starting from chapter number 2 from the Proteus, you should also start to read that chapter, where in the first section we'll try to classify classifications. We need to start to know about the classification of discrete time signals. As there are some classification of continuous time signals, there are some classification for the discrete time signals as well, though most of the terms could be very much similar to the continuous time signals as well. So I believe that most of the terms are very much known to you. Still, I want to recall those terms so that you have a better understanding, clear idea from the graphical representation point of view as well. Okay, first of all, there are different ways you can classify your signal: from the energy perspective, from the time invariancy, from the linearity perspective, from the stability, instability, and whether this is a causal signal, non-causal signal. So there are a lot of types of classifications. So step by step, we try to discuss and try to give the examples with some graphical representation, so that you can understand it. So first of all, from the energy point of view, whether the signal is an energy signal or not, by definition, the energy E of a signal xn is defined as E is equivalent to xn squared, the modulus of that, for the samples, for the summation of the samples from -infinity to +infinity. So hopefully you understand that we have different stems in the different position. We need to take all the samples. For all the samples, we need to square of that. If we have a negative sample as well, it will be negative positive, because it also have the energy. Whether this is a positive or negative, it always contains some energy. And then we need to square of that for each and every samples. We need to add all those samples, and it gives us the energy of the sequences. How we could relate this energy? How could we relate this equation with our conventional idea of the energy? Okay, let me discuss it here. What about the, so I'm just representing the equation for the energy. I'll try to make you understand why this equation, how you can relate your conventional idea with that equation. Let's say we have a circuit like this, a simple load, and the load is a single resistor, and for that we are supplying a voltage Vt. This is a continuous time voltage, that means instantaneous voltage, and definitely we'll have an instantaneous current for that. Okay, from our conventional idea, we know that the equation, we know the equation from the Ohm's law. This is V is equals to IR, and we also know that the instantaneous power is equals to VI. Instantaneous the power, we are having this because since there is no inductive part, so there is no phase delay or phase lagging or leading, so that's why there is no point of putting the cos theta. So the P power is equals to VI. This is our conventional idea. From there we can write it very easily, because from this Ohm's law we can write that the I can be replaced as a V by R. From there we can write that, okay, the P or the continuous power, instantaneous power, is equals to V square T by R. Here, if the R is equals to 1 ohm, if you let that 1 ohm, in that case we can write it like this: the instantaneous power is equals to V square T. From the concept of the power with the work, we know that P is equals to W by T. So work done with a period of time is equals to our power, where work done is equals to P multiplied with the time. As you know that if we have some, let's say, some metal or some weight, and this is the land, so of course this mass should have some energy which will give us some promise to do some work. When you throw these elements, or if you make it release, then it will definitely fall down and it will do some work. So this work and the energy, they are equal. Energy is the promise of doing the work. So work is the expression or the outcome of the energy. Okay. So here we can represent is the energy is equals to P into T. Here the energy, we know that this, so this equation can be represented for the instantaneous power. We can represent is the PT dt for minus infinity to plus infinity time. So for an infinite period of time, we can represent our energy like that, where we already mentioned that the instantaneous power is nothing but V square T. So we have replaced it by the V square T, and dt is there. And now eventually this is the equation. So E is equals to Vt square V square T dt for the time period from minus infinity to plus infinity. This is for continuous time signal. Now what about the discrete time signal? It can be represented like this. For the discrete time, of course, this time period will be discretized for n is equals to minus infinity to plus infinity, and we do not need any dt because we have discretized those, and we do not need any integration because we are making summation. And what is V square T? Nothing but this xn, x square n, because these xn actually represent different voltages. The stem, this stem is nothing but different voltage we are getting to the circuits. In a circuit, in a discrete circuit, what are the voltage value you are getting is the consequences of the circuit output or inputs. So this is our xn. So x0, we need to square of that plus x1, we need to square of those, x2, we need to square of those. And this is called the summation of all the samples. You need to sum up with a value from minus infinity to plus infinity. And that represent our energy signal. So I believe that you understand why we are representing it in the equation by this format. We can correlate with our classical representation of the energy signal. So for having an energy signal, if the signals need to be an energy signal, then if E is finite, finite means not infinite, then Xn is called the energy signal. If E, hello, assalamu alaikum.
Yes, sir.
Okay. Yeah, probably there's some problem with the internet. It's missing some part. Okay, let me start it again. Yes. Could you please, probably one of your friends already raised the hand. Could you please mention what is the question?
Sir, I raised the hand.
Yeah.
I didn't get the fact that why are we taking R equal 1 ohm? Because we are generalizing the equation for E, then why are we ignoring the effect of R by assuming it's 1 ohm?
Okay. Yeah, this is very good question. We can relate it like this. Whenever we are taking a circuit, this is a physical circuit, let's say RLC circuit. Let me take the annotation bar. So when we are taking the RLC circuit, in that case, resistive circuit, we are not taking the RLC circuit. That could be another question. So why we are not taking RLC circuit? So these are I should say the equivalent or proportional presentation. In this case, whether you have R is equals to 1 or not, whatever the cases, ultimately the output is the voltage. Depending on the voltage for the digital circuit, ultimately we got the stem. It actually not depends on, we are getting the output. We are getting the output, and let's that this output is for the value R is equals to 1. There is no harm with that, because what is your outcome? Let's say from the voice signal, you have the microphone with the voice, you are getting some output, and that is your voltage outcome. And if we let that, this is for the value of R is equals to 1 ohm, do we have any problem? Basically, we don't have any problem. You got that?
Yes, sir.
Yes. That is why we are just make it simple and try to make it, try to relate it with our classical representation. Okay. You can take R is equals to any value. However, R equals to 1 represent the voltage. You have actually the output, and output, what is the output? The voltage. And if you want to convert it to the energy or the power, it will be very helpful and convenient to understand if you take R is equals to 1. So that's why we write it, let R is equals to 1 ohm. Fundamental, in a fundamental case, that is not always that R is equals to 1 in a circuit. But whenever we are talking about the digital signal processing or analog signal, even analog signal processing, we are taking the voltage, we are getting the voltage. So relating to that, you can always make R is equals to 1 or proportional to the 1 value. Okay, so there is no harm with that. Okay. So I believe that I have already covered up to this, isn't it? I need a response. I have already covered up to this, isn't it?
Yes, sir.
Okay. So I have already mentioned that if E is finite, then it is called a energy signal. For example, I have already given one example. Let's say we have this kind of signal, whatever the value, this is 0th sample, first sample, second sample. Of course, this is an it has a finite energy, and that's why this is a energy signal. If we have samples up to infinity, of course, the summation square of summation of infinite value from 0 to, let's say, 0 to infinity, that also goes to a infinite value, and then it is not a energy signal. So to be a energy signal, the summation of this should be finite, and then it is called the energy signal. That is the definition of the energy signal. What about the power signal? Similar to that, if the power signal can be represented by this equation from the convention, we also know that what is the power signal? We know that we have the energy divided by time period. So we have this energy. This is an energy signal, and divided by time. What is the time? Time is from minus n is from minus capital N to plus capital N. So what is the total time period? The total time period is twice capital N plus 1, because the 0th sample is also a sample. So you have total twice n plus 1. That's why we need to divide it by twice n plus 1. And if you want to cover the whole spectrum from minus infinity to plus infinity, then it will be from minus infinity to plus infinity. So how do you write it like this? Divided by infinity plus 1. It is twice infinity plus 1. It actually not been represented like this. That is why we are making a limit. N is up to infinity. So we have written like this, xn. This is the energy where we are making a summation from minus infinity. Now the minus infinity, we are making a finite value from minus n to plus n, so that we can write it like this, twice n plus 1. And now we are making a limit of capital N, where capital N goes to infinity. That gives us the power signal. Now this power signal, whether this is a power signal or not, if E is a finite value, try to understand, if E is finite, that means this part is a finite one, then it will be divided by an infinite number. That means n is from minus infinity to plus infinity. That means the P goes to very close to 0. That means if E is finite, then P goes to 0, and that is obvious, and that is not a power signal. On the other hand, if E is infinite, then there is two possibilities. The P could be finite or infinite. If E is extremely infinite, then there are two possibilities. The P could be finite or P could be infinite. If P is finite, then that is called the power signal. For example, if you have the signal like this, a periodic signal. Let's say if you have a periodic signal from minus infinity to plus infinity, okay? I'm putting it dot, 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 so that it means that it starts from minus infinity to plus infinity. I'm asking to the class whether this is an energy signal. Is it an energy signal? from the discrete signal point of view, we have the stem like this. All through, you have the stem like this, from minus infinity to plus infinity. Yes. 72.
Sir, it is a power signal.
Is that an energy signal, first of all?
No, sir, it's not an energy.
Why not?
It is extending in the range of infinity.
Exactly.
Since
Yeah, since the n, when we are making the summation for n is equals to minus infinity plus infinity for x square n modulus, of course it gives an infinite value. That's why this is not an energy signal. Thank you. And why this is a power signal?
sir, since energy is infinite, so since the energy is infinite, so I think that the power which we will obtain will be finite
Can you prove that?
in value.
Can you prove that? Because I have already mentioned that if E is infinite, there are two possibilities. P could be finite or infinite. So how do you prove that this is a finite power, or it is a power signal? Okay, let's take this example in this way. Take up to this. Since this is a periodic signal, we are taking this period, the first period. And for the first period, whether this is a power signal or not, that means a finite power. Do you have the finite power or not? The answer is yes, we have a finite power, because definitely we have finite energy, and we can divide it with a finite number of samples. For example, what are the number of samples? 1, 2, 3, 4, 5, 6, 7, 8. The 9 belongs to the next. So 8 is the sample number. And what is the energy, total energy, square of that? Okay, so let's put it like this. E divided by 8, that is the power of the first cycle. Then what is the power of the second cycle? Must be the same, since this is a periodic signal. So P is equals to E divided by 8, the same. So combinedly, what is the power? Combinedly for two cycles, what is the power? The P prime is equals to E divided by 8 plus E divided by 8 divided by 2, because you have the total value is 2. Okay, number of samples. So you can find that you are averaging all the time. You are averaging all the time. Or you can say that, you can also write in this way, E plus E divided by 16. That is also true. E plus E divided by 16. If you want to count the third cycle, then you need to write it like E divided by 24. So in that way, since E divided by 8 is a finite value, of course, thrice E divided by 24 is also is equals to E by 8. So always the power should be is equals to the E by 8. That means the power of the single cycle. The power is equals to E divided by 8 for the full signal from minus infinity to plus infinity. If I conclude it like this, even though a periodic signal is not periodic signal having the sample from minus infinity to plus infinity is not an energy signal, but it is a power signal. So you need to prove it, or you need to understand that. Is that clear? A periodic signal, whether this is from the minus infinity to the plus infinity time duration, having the time duration from -infinity to +infinity, even though that is a power signal, and that is true for each and every case. Okay, and that actually been mentioned in the subsequent section. I have discussed it already. So please go through this example from the Procreus book. You will get some example on the power signal and energy signal that will make your idea more clear. Okay. Then symmetric and asymmetric signal. As you know that we can represent our signal like a cos signal or sinusoidal signal, sine signal. So one of them are the even function and another one is the odd function. So in that way, we can represent the signal in a even symmetry or by the odd symmetry. Even symmetry means symmetric and odd symmetry means asymmetric signal. I believe that you understand those part very easily. Just you have already those kind of experience in your last semester. So not to mention anything. So this is, of course, you have the symmetry, the cos signals. Whenever we have the cos signal, the symmetry, we have the signal symmetry like this. X minus n is equals to xn. That means this signal is equals to this signal, and so on and so forth. For the antisymmetry or the odd symmetry, this is sinusoidal signal. This one is equals to this one, but in the having the negative sign, negative amplitude. So it is equivalent to the sine, and this is equivalent to the cos. So cos represent the symmetry or the even, and the sine represent the antisymmetry or the odd signal. So in future, maybe after the mid, you need this kind of concept. So that's why this is really important to understand the facts. Okay, how we can represent a particular sequence with even symmetry or even symmetry and odd symmetry. Let's think in a way. You have a signal xn, arbitrary signal xn, any sort of combination of any signals. Let's think that it is a combination of even symmetry and odd symmetry. We have, and now x minus n is equals to E minus n O minus n, odd symmetry. According to the fact, we know that since this is an even symmetry, E minus n, that means in the opposite direction, it could be written as the same as En. For odd symmetry, it is equals to minus On. We have represented just before. Okay, so we know this fact for the antisymmetry, and we know this fact for the symmetry. So we have applied that formula in this equation number 2. Now we have equation number 1 and we have equation number 2, from where you can represent, you can find the value of En. So you can draw the xn. You can also draw x minus n of that signal. The xn is not an even signal or odd signal. This is a arbitrary signal, arbitrarily represented signal. So from there, what is the step number 1? You will draw xn, you will draw x minus n. Then by adding those two signals and divided by 2 will give you the sequences of even symmetry or even signal. That means like a causal signal. Similarly, you can also find what is the odd symmetry signal. So you can make a combination of these two two equation. By this using two equation, you can also find what is the value of odd symmetry there. We need different sort of manipulations during this signal processing, and few manipulations are very important. So we'll discuss those things with a graphical representation. We'll start it today, but it will take some time to finish up all those presentation. Okay, so first of all, we'll talk about the transformation of the independent variable. So independent variable is nothing but the time variable. So first of all, we'll talk about the shifting operation. So let's say we have our xn, and this is xn minus 4. How to represent that? So try to understand this fact. This is very important. Let's say you are giving xn to a system. This tau represents a system, and you have the output yn, where yn is equals to xn minus 4. That means this tau shift delayed your system by 4 samples. Delayed your system with 4 samples. Here you can find that this is the 0th sample. Let's say what is the value of the 0th sample? 1, 1, 1, 1, and then let's say this 0.8 and lower than 0.8 and lower than 0.8 and so on and so forth. Now this sample is now delayed with 4 samples. Previously it was at the location of 0. Now it is shifted to the location with 4. So now it's shifted. If you consider that you are at this moment in a digital signal processor point of view, when you are giving your xn, the current point means you are at the 0th sample. That is the sample this system is facing now. But if you delayed it by 4 sample, now 4 sample means this is the 0th one, 1, 2, 3, 4. This sample is now at the 0th location. That means your system will face this system. So these are the present, these are the future samples that will be faced by this system, and those are the past. Past means they have already gone through the system. They have already processed by the system. Now, so this is a delayed system. So how we can calculate those things? These are the graphical representation. How do we calculate practically the positions? So let me write it like this: yn is equals to x n minus 4. Now, what is your target? Your target is to draw yn. So let me draw it here. This is what? This is my yn. This is the 0th position of yn, first, second, third, -1, -2, something like that. Okay. Now, if I want to find the y0, that means what will be the sample at this point? How we could find it? So I need to find y0. N is 0. N of y is 0. So we are targeting this 0th position is equals to x 0 minus 4. That is equals to x minus 4. What is the value of x minus 4? X minus 4. That means x is a function. Where is x? This is x. The mother function is x. And this shows the point or the sequence. Where is -4? this is -4. You understand? This is -4. So what is the value? The value is this. So I will put that value at that location. I would put this value where at this location, because I am drawing the yn. Let me write y1. That means I am now targeting y1. The value is x1 minus 4. That is equals to x minus 3. Where is that -3? This is from x, is the mother function. So this is that -3. Then what would be the value? This would be the value. Similarly, you can find all those samples and you can draw the total spectrum of yn. If I made it, if I draw the conclusion, we can write that if we have xn minus k, where k is the value, where k is greater than 0, that means a positive value. In that case, in which direction the signal will shift? In which direction? xn minus k. In which direction the signal will shift? Any of you? If k is equals to 1, 2, 3, 4, 5, any value.
To the right direction.
To the right direction. That means it actually delayed. It will be delayed. Similarly, if we put like n plus 2, what does it mean? It will be forwarded. It will be forwarded. Forwarded means this sample will forward it to the 0th sample. This point will be forwarded like this, and this point will be forwarded to. All the points will be forwarded to samples to the left. How could you find the value? Similarly, yn is equals to xn plus 2. So if I want to find the 0th sample of y, that is equivalent to n means 0 plus 2. That means x2. Where is that 2? This is from your mother function is this. That means that is the sample at the y is equals to 0. So if this is your yn, this is the location of 0, the value of that would be is equals to this one. That will come to this point. Similarly, the previous one will be there. So I can draw it like this, 1, 2, 3, 4, and after that it will be decaying like this. So this is nothing but yn is equals to xn plus 2. This is how we can shift our signal to the right or left. So this is called transformation. Transformation of independent variable. Okay, we can also have the folding operation. What is folding operation? I'm not sure whether we have told it or not. So we have xn. If we want to fold it, so folding it, that it is minus n. This is called the folding operation. You can fold it. So what does this mean? How we can represent the folding operation? Okay, this is the equation. So we have our xn. Let's say we take an xn. The xn may looks like this. Okay, so this is 0, 1, 2, 3. Now our job is to draw the folded version of this xn. So folded means we have also mentioned that this is x minus n. Now your yn is equals to x minus n. This folding operation is also an operation. Folding operation is also one kind of operation. So we need to do this operation. So if I want to find y0, what will be the value? X minus 0, that means it is equivalent to x0. So the same sample, it will be printed on the 0th position. Okay, fine. If I want to find y1, that means what will be at the first point? This will be x minus 1. Where is minus 1? This is minus 1, minus 2, minus 3. Is there any value in the minus 1? No. Is there any value at x minus 1 location? No, there is no value. So that means at y1, we don't have any value. What about y2? Definitely, we have x minus 2 and we don't have any value. So we doesn't have any value in the positive side. Let's check with the negative one. Y minus 1 is equals to what? X minus minus, so plus 1. What is the value there? Okay, whatever the value, we can put it like this. What is y minus 2? This is equals to x2. And what is x2? We can present it. So the other one must be like this. So this is the folding operation. Folding means this 0th sample will be remain the same, and the left side sample will move to the right side, and the right side sample will be moved to the left side sample will be moved to the right side. This is the folding operation. Okay, so this is also very important in future perspective. So it can be mentioned that if we have the time delay means it can be delaying or it can be advancing. So advancing means x n plus k. This is advancing, and delaying means n minus k. And folding operation, if we talk about these two operations, they are not commutative. Means that if you do the time delay operation and then folding operation is not equal to the doing the folding operation and then time delay operation. So if I have doing the thing like the time delay and then folding operation, you can't say that folding operation and then time delay will give you the same result. So you need to be careful about this. So this is not a linear combination. This is a non-linear combination. Okay, we can stop here today. In the next class, we'll give the example of this. The example by which we can understand they are not commutative in nature, and then we'll move for different perspective or different classification of downsampling, upsampling, and their perspective, as well as the time variancy of the signals in the next class, inshallah. Okay, then thank you very much for your participation. Hope to see you in the next class, inshallah.